that this talk will go smooth. Okay. Got it. So I'm hoping that this talk will go smooth and the internet and my sore throat will not bother us. As you all know, that the talk is about pattern membranes, and the topic being very new, it was very, very interesting to explore. So I'm hoping that you will enjoy the talk. I have tried to keep it simple, but of course there would be technical discussion as well. So globally, as the world water, so are my slides moving forward or not?
No, it's still the first slide that we can view.
Yes, for me as well.
Maybe if you stop sharing and try it again.
Okay. Okay, now it's starting.
Yeah, now it's working. Perfect.
Let me start. Yeah. So as the world water resources are getting depleted year by year, this has led to actually leave about 1 billion of people without access to clean water. And on top of that, human consumption is even further polluting the available groundwater. And all of this has led to a growing number of different pollutants in the wastewater, ranging from oil emulsions, bacteria, and organics to inorganics and various salts. And all of these needs to be separated in order to reuse the wastewater. And for that, one of the major separation technologies include using membranes. And as most of you know, that these acts as selective barrier for these different pollutants. So based on the pore sizes of these membranes, we are able to retain these pollutants and to obtain the fresh treated water, which can be used for household and agricultural purposes. But as every technology comes with its own challenges, the problem in this case was the deposition of these pollutants, which we also know as foulants on top of these membranes, which reduces the amount of the fresh or treated water. So to counter these problems, one of the approaches was to create these surface structures on top of these membranes. This not only provides additional surface area, but it also increases the local surface velocities. This reduces the deposition of these foulants on the membrane, providing us more amount of fresh and treated water. So there are a number of different methods to create these surface structures on the membranes, while the method we used was actually a modification of a conventional phase inversion process, which I'm hoping that you had an introduction at some point, or you might be working with the phase inversion. So just as a recap, during the conventional phase inversion process, the polymer solution is added into the casting knife, a conventional one, which casts a wet polymer film. And then we can immerse it in a non-solvent pad, which is usually water. And by immersion, it creates phase inversion and solidifies the membrane. But our modification included the addition of a patterned casting knife and spraying the non-solvent, which I'm repeating is the water. So, and then after this casting, then we immerse our membrane in the non-solvent bath, which means if we take a closer look, then we could attach the patterned casting knife with the already conventional knife. And as soon as this knife creates these patterns on top of these wet film, we could spray the non-solvent to immediately solidify these patterns. And we termed this method as SNIPs. So why this method is better? So first of all, it was very simple and effective modification of the conventional process. And about the importance of this point, I will again come to it later in the presentation. Also, as compared to other patterning methods, we could create patterns on the active side. because you can also create patterns by pouring your solution on a patterned mold. But in that case, the patterns will be formed on the backside, which we do not want. Also, it does not create any reduction in the pore size or porosity of the membrane, which is possible if you are going to imprint these patterns. So imprinting includes that where an already formed membrane, on top of that, you can imprint the patterns with a mold at high pressure and temperatures for a certain time. In terms of surface features, the other methods could only produce nanoscale features ranging from 50 to 300 nanometers, but SNPs had the potential to create micro-level surface patterns. So therefore, this talk will mainly be focusing on further exploring the SNPs. And the talk would be actually divided in two phases. The first phase will be focusing on obtaining a fundamental understanding of this SNPs process itself, and then to see the effect of the resulting membranes on the fouling of these membranes. And for that, membranes were prepared in microfiltration and ultrafiltration range. And then in the phase of the talk, we wanted to further exploit or to push the limit of the SNPs process by preparing the membranes towards a denser spectrum, which mainly included nanofiltration and forward osmosis. So starting with the first phase, which will focus on actually achieving the fundamental understanding of the process. The initial experiments or the trial experiments showed there will always be a need of minimum viscosity of the solution, which you might have an idea could be adjusted by changing the polymer concentration. So which means that a threshold minimum viscosity is needed, because at lower viscosity, the patterns will just relapse very quickly, even before the non-solvent spraying can solidify patterns. So therefore, with the optimum viscosity, we could create the patterns. So from this point onward, to see the potential of SNPs in creating different pattern shapes and dimensions. And for that, polyacrylonitrides were prepared in microfiltration range. I see the internet connection is unstable, but I hope that everything is going fine. So we made polyacrylonitrile membranes for microfiltration range. So initially, the conceptual designs of different pattern shapes and different dimensions be easily transferred toward 3D printing these knives, and then to prepare pan-based membranes. So all of these membranes resulted in typical asymmetric morphology, which we always expect for these phase inversion-based membranes. And that was very interesting that the morphology was not changing even by patterning. Then in terms of transferring these features of what we design and what we achieving on the membranes, of course, this what we call as intrinsic solidification always results in polymer shrinkage. And because of that, definitely not achieve 100%, but what we got in this case was about 45 to 80% of pattern height application on the final membranes as compared to what was on the pattern knife. So further characterization of these membranes showed higher bulk porosity, mean pore size, and higher surface area for these pattern membranes as compared to the flat membranes. And specifically, it was increasing with increase in the pattern height. And we could see exactly the same, which was translated in their. So with increase in the surface area, the pure water permeance was increased. But of course, there would be an optimum to avoid a drastic rejection. But before moving forward, this increase in the bulk porosity and pore size for flat spray membranes. So these were not patterned only, and the bulk porosity increased drastically, and it was very intriguing. So the SEM images did show higher total thickness, surface porosity for these flat, and in terms of performance, the permeance was increased by 3%, but of course there was decline in the rejections. So this showed that this patterning and spraying, this permeance increase is actually due to both this increase in the surface area, but also due to spraying, because spraying is also altering the structure of the membrane. But the similar increase in this surface property was not observed for the rest of the pattern. So it was important to understand actually that what was happening on the fundamental or on the basic level, and therefore it was important to understand the phase in these membranes. In case of flat sprayed membrane, if we could calculate the amount of water sprayed on the membrane, and based on that, enough to completely solidify the membrane throughout the cross section, and therefore there was very solvent non-solvent exchange, and that can lead to higher surface porosity. But in case of pattern membranes, the amount of water sprayed was to solidify just the top layer, and the rest of the phase inversion was taking in the coagulation bath. And that is what was altering during this phase inversion process. So with the increase in the pattern height, it was then again partially defying the top layer because the non-solvent and solvent from all of the sides could enrich the non-solvent and delay phase inversion. So there was very common of the phase inversion. However, it could give us that and spraying is also a process, and it is not equal to the conventional phase inversion that we have. With this, we wanted, it was important to the same estimates could also be used for other polymer or solvent systems, because generally also in phase inversion, oh, the internet connection is unstable. Okay, so because generally also in phase inversion, the conclusions, if we draw conclusions on the basis of only one polymer solvent system, they cannot be generalized to each of polymer. And for that, we used PVDF-based means to prepare the ultrafiltration range. So as in previously, just increasing viscosity by increasing the polymer concentration did not result in homogeneous patterns. And that was mainly because of two phase inversion of PVDF as compared to polyacrylonitrile, which we used earlier. That is because being very slow in phase inversing, the formed patterns will not immediately solidify. So the answer could be to speed up the phase inversion. For that purpose, addition of hydrophilic additives, which can be PVP, adding them in the casting solution can disturb the thermodynamic stability of casting solvent and can accelerate the phase inversion. And similarly, water, which is already or non-solvent, can do the same and phase inversion for these membranes. And by addition of these in the solvent resulted in patterning of these membranes for higher PVDF applications, which was also in their performance where the permeance increased for higher polymer content, while actually opposite could have been happening if it was a conventional process that increases with increasing the polymer concentration. Similarly, choice or the molecular weight of the polymer and the choice of the casting solvent were also assessed as very important key factors, because polymers with lower molecular weights will be beneficially phase inversion, therefore supporting our hypothesis again, and choosing a solvent which has better miscibility with the non-solvent, which is will also have rapid solvent non-solvent exchange, and of course in better better patterns, for example using NMP. Another interesting alternative to using water in the casting solution was using lithium chloride. So using chloride resulted in better pattern heights and better pattern formation. And that was mainly because of the ability of lithium to form complexes with the solvent, which in this case was DMF. So formation of these complexes could reduce solvent power of DMF, and therefore disturbing or reducing thermodynamic stability and increasing the solution viscosity. So this was another alternative additive which we could explore. So now with this optimum composition we have, and now we can have patterned PVDF membranes, we prepared different PVDF ultrafiltration membranes, again with using different 3D printed casting knives. And two of them were prepared with very large interpattern distances, which are highlighted here. I'm going to check quickly my chart. Okay, so everything is fine. Let's move forward. So we prepared, the two of them were prepared with larger interpattern distances, and the rest of them were homogeneously patterned. Similarly, the performance showed a similar, oh shit. Yeah. So the performance actually again showed a similar behavior where the permeances were increased for homogeneously patterned membranes. In terms of pore size, again, the pore sizes were patterned membranes as compared to flat membranes. Interestingly, the flat sprayed membrane and the membranes with wider interpattern distances show much wider distributions, which actually explain their low rejections. With this, we could see that in case of PVDF, the pattern height replication was only about 30 to 40%. But it also shows us that with choosing each time a different polymer system, we will always need an optimization, and which would actually help us to tune the setup. So all of this, we could actually understand the SNPs process, that SNPs able to replicate the pattern dimensions with an acceptable accuracy. Simultaneously, patterning and spraying was altering the conventional phase inversion process, which was actually changing the bulk porosity and pore size of these patterned membranes. This additional area was very beneficial in increasing the permeance of these membranes. On the other hand, there is no restriction in choosing a polymer-solvent system, and more importantly, controlling all of these different phase enters, for example, choosing what casting solvent, a molecular weight of the polymer is the key to better pattern formation. So with all of the understanding of only about the SNPs process itself, could now finally study the following behavior over these structures. So this was mainly done by using cross-flow ultrafiltration of these previously or just mentioned PVDF pattern membranes in cross-flow filtration using proteins as foulants, and also in membrane bioreactor municipal wastewater. During of cross-flow, The permeance decline was mainly due to the deposition of foulants, but it could be divided in 3 phases, where the first phase was actually rapid absorption and concentration polarization on the membrane surface due to the convective flows towards the membrane during filtration, which was followed by a second phase where foulants are gradually depositing on the membrane surface, covering the entire surface area until a third phase is reached, where constant foulant layer is formed for that particular driving force, and the permeance starts to reach a constant value, which we call a steady state. And this third phase was not reached for homogeneously patterned membranes as compared to flat and largely or widely patterned membranes. So, and further investigate, as in crossflow, these pattern lines which we create can be placed or oriented in both directions to the direction of flow. So if the direction is flow is in X direction, the pattern lines could be placed both in perpendicular and parallel directions. So we studied the following both directions. First, by the critical pressure, which was based on that during filtration, you start the filtration and the foulants are deposited on the membrane surface. But at that, increasing the pressure will increase the flux through that membrane. But the filtration keeps on, and with time, as the as keeps on getting deposited on the membrane surface, covering the surface area, further in the pressure will not increase the flux anymore. And identification of this point can indicate the formation of a cake layer. So this is the theory to determine the critical pressure. And secondly, computational fluid dynamics was used to study the hydrodynamics in. So in this crossflow was in X direction, and the patterns could be placed in parallel and perpendicular direction, both. So starting with the critical pressure, it was determined by, so the critical pressure was determined by in pressure stepwise, and then observing the flux during this each step. So here, this stepwise increase is shown in on secondary Y, and the corresponding flux decline can be shown with these black lines. The red dotted lines here show the critical pressure, and this value of critical pressure was obtained was higher for these homogeneously patterned membranes as compared to membranes, and this higher is actually indicating delayed cake layer formation for these membranes. The simulations in a parallel direction for these membranes showed higher velocity regions more closer to the mass, but as there were no changes in these velocity contours, it suggests very minimal effect of surface hydrodynamics. And improved results were mainly due to higher surface area. If you could remember my previous, the surface area for a better membrane was about 200 to 4% higher. So this surface area can reduce the local flux, which is distributed over the membrane surface. And that can reduce the deposition of foulants. On top of that, the deposition of foulants, the additional area you create by patterning can still remain available for filtration of the feed after the foulants deposition. So now coming towards the same observation for perpendicular direction, similarly, the critical pressure was again higher for these homogeneously patterned membranes. But The value was highest for triangular pattern membrane as compared to rectangular ones, suggesting now that there is more effect of hydrodynamics. So this could be actually formed by the CFD simulation, which showed higher velocities for triangular membranes, and no dead zones were observed for triangular pattern membrane, which could be in these widely patterned membranes or rectangular membranes. So suggest that particular orientation gives better hydrodynamics to control the fouling, and the local velocities at these pattern apexes are higher in case of perpendicular as compared to parallel orientation. So further, the fouling potential was then now further studied by hybridizing this patterning with module vibration. Vibration of module was another technology which we had in our lab, and we combined it with surface patterning of our membranes in membrane bioreactors. So similarly, total critical flux and critical flux for irreversibility was determined for these PVDF membranes. Critical flux is also a similar concept based as critical pressure, where flux was increased in stepwise manner, and we observed the pressure. There were two main scenarios for which this was determined when patterning was applied in membrane bioreactors and when it was combined with module vibration. The critical flux values are shown here, and these values were doubled for patterned membranes as compared to the flat membranes. Both the critical flux, total critical flux, and critical flux for MD were both, and that was mainly because of already explained increase in the surface area. But addition of vibration could further improve the performance of these membranes. Although there was no significant increase in critical flux, but the critical flux for irreversibility was increased by a significant margin, and suggesting that this addition of was very, very effective in continuously disrupting this boundary layer formed at the membrane interface, and therefore it was effective in reversing or removing the already present foulants on the membrane, which could be shown experimentally by this higher critical reversibility. This CFD stimulation of these membranes during the vibration, you can see the formation of vortices during the vibration, and these vortices were connected away from the membrane surface, and that is highly beneficial for removing these foulants which are already deposited on the membrane surface. With this, we could have a basic understanding that patterning of the membranes can disturb fouling over these membranes, therefore delaying the cake layer formation as well. This is mainly because of the effect of higher surface, also because of hydrodynamics. So both of these factors are contributing in their own perspectives. Perpendicular orientation was better in improving the hydrodynamics, but parallel orientation had dominant effect of this increased surface area. In terms of surface features or surface pattern dimensions or shapes, triangular patterns were less prone to dead zones and were providing better hydrodynamics, but rectangular patterns were more effective for increasing the surface area of the membrane. So depending on your application, you can choose the pattern shape. And also, these membranes were similarly effective in wastewater treatment and hybridizing and combining it having more vibration, brought us more in controlling the flow over these membranes. So with all of this overall understanding, now we could finish or conclude our first phase, that we had an fundamental understanding of the process, and now we know that how the fouling takes place, or what is the anti-fouling mechanism over these membranes. So we could move towards a second phase of this talk, which will be now by using these membranes for a relatively different process, which is osmotically driven membrane process, meaning forward osmosis. So giving a short introduction that when a membrane comes in contact with the draw solution with the high osmotic pressure and a feed solution side with low osmotic pressure, water gets transported from the feed side to the draw solution side to balance out. But due to this, some of the salt also passes from side to the feed side, which should be kept as minimum as possible, and it is known as reverse salt flux. But in this forward osmosis process, the problem arises when the salt in the draw solution starts getting accumulated in this porous support, and any presence of the foulants in the feed solution, they can get deposited on the membrane surface, and this actually results in concentration polarization. This concentration polarization can be internal and also be external, and this actually reduces the osmotic pressure difference, and which affect the water flux, because the water flux in forward osmosis is mainly because of this difference in the osmotic pressure. Therefore, in this talk, or in this research, we replace these conventional cellulose triacetate-based membranes with patterned membranes. Excuse me for a second, please. Okay, sorry for this. So by replacing the conventional membranes with the CTA membranes, pattern membranes, the membranes were prepared without any additives, and you can see the membranes here. Very apologies for this. I think now I'm a little bit better. My apologies. The membranes were prepared without any additives, and as observed previously, the pattern membranes had higher bulk porosity. Yes. The pattern membranes had higher bulk porosity, and because the phase inversion was getting altered because of, I already explained, the spraying and the patterning, we could have the pattern membranes had the top layer, or the dense top layer, with higher thickness for the pattern membranes. The performance comparison of these the performance comparison of these membranes showed higher water flux and lower reverse salt flux for these patterned membranes. And the, the performance, because this water flux, this increase in the water flux was mainly because of the increase in the surface area of these membranes. But it was also interesting to see the effect of the internal concentration polarization in these membranes. And this ICP effect could be determined by determining the structural parameter of these membranes. The structural parameter was mainly dependent on tortuosity and porosity of these membranes. So by
excuse me, Dr. Ayesha. I believe if you are not feeling well, we can skip this second part. We are already quite grateful to you that you spare time and for this webinar, despite you were not well, but still you made it. So we are thankful. So how about we move to the conclusions? And I have I see there is a huge interest. There are more than 140 participants. So would you be able to answer a couple of questions?
Definitely then move on to the conclusions just by giving a short overview.
Yes.
My very much apologies